Hello, everyone, and welcome back to the second installment of the first lesson. My name is Micah Small. I am your CFI, guiding you through, and we're going to look at principles of flight this time, and hoping to get you to earn your private pilot certificate. So, again, starting out with principles of flight, we're going to look at the characteristic forces of flight, why and how the airplane performs the way it does. Okay, why? It's because the competent pilot must have a well-founded concept of these forces which act upon the airplane and the advantageous use of these forces as well as the limitations of the particular airplane. Okay, so the content here, forces of flight, airfoil design, wing platform, stability and controllability, turning tendencies, load factors in airplane design, and wingtip vortices. So another installment of some very, very important things that we need to be very good at our job as pilots as we learn and progress through the ranks, okay? So let's take a look at the four forces of flight. Lift is the upward force due to the effects of airflow over or under the wing. Weight is opposite lift, and it's caused by the downward pull of gravity, okay? Thrust is the forward force propelling the aircraft through the air, and drag opposes thrusts, backward force limiting the airplane's speed. All right. So the chord line is an imaginary straight line joining the leading and trailing edges of an airfoil. The relative wind is the direction of movement of the wind relative to the aircraft's flight path. And then the angle of attack is the angle between that chord line and the relative wind. Looking at the principles of lift, the first one we're looking at is Bernoulli's principle. As the velocity of a fluid, in this case air, increases, its pressure decreases. The curvature of the upper portion of the wing, okay, that's what causes it to increase in speed, velocity, so the pressure decreases, creating a low pressure on top of the wing, and then we know that pressure wants to go from high to low, so it pushes upward on the bottom of the wing to create lift and push us up through the air, okay? The other side of that is Newton's third law, and that means that every action has an equal and opposite reaction. So the downwash or air striking lower surface of the wing then forces it upward. All right, an airfoil is any surface providing aerodynamic force when it interacts with a moving stream of air, okay? What that means is the wing's shape takes advantage of Newton's laws and Bernoulli's principle. So the curvature on the upper portion, the air speeds up over top of that, creating a low pressure system. And then there's a downward and backward flow that pulls the air off there to create that low pressure system. And then the air striking the bottom of that wing when it's inclined a little bit is going to force it upwards as that air tries to go from an area of high pressure under the wing to an area of low pressure on top of the wing. All right, so that is basically, it's the coefficient of lift there, is what you're looking at in that that equation. That's a really fancy way to just say that, well, what we just said, Bernoulli's principle and Newton's third law creates lift on a wing. So the pilot can control the angle of attack. Changing the pitch of the airplane changes that angle of attack, and then we can increase or decrease the velocity of wind going over the top of the wing, and that can in turn lift or lower the wing, okay? So the airspeed lift is proportional to the square of the airspeed is basically what we take away from this. And then the surface area, we look at that, and it's the flaps and slats can increase the surface area. Otherwise, S is constant during cruise. All right, so weight. The force of gravity acts vertically through the center of gravity toward the center of the Earth. When lift is equal to weight, the plane doesn't gain or lose any altitude. Okay, if the weight is greater than lift, the plane descends. If the lift is greater than weight, that plane is therefore going to climb. The forward force opposing drag, that is thrust. Okay, it's mass times acceleration is force, and thrust is that particular force. Okay, the airplane will continue to accelerate until thrust is equal to drag. So if thrust is greater than drag, the plane will accelerate. If thrust is less than drag, the plane will decelerate. All right, so when we're talking about drag, we have a couple different types of drag that we can talk about. So a parasite drag that surfaces interfering with smooth airflow. So just the form factor of the aircraft, its size, its shape, and then the interference then would be the currents of air interacting in, around, and against each other. And then there's a skin friction. So any friction or anything protruding from the skin, such as rivets or a step hanging off the side or anything like that that's built into the airplane, that is a parasite drag. It is not drag that is directly induced by production of lift, which brings me to induced drag, which means that is a byproduct of lift. So the induced drag is directly connected to the amount of lift that the aircraft connects. So, and it can be caused by a creation of like a wingtip vortices, as we'll get into more of that information down the road as well. So the total drag actually is going to be then the combination of the parasitic drag plus the induced drag, okay? And then we're going to talk about a couple of different areas of command, we call it. It's how we use the power and these forces to work together to create lift and speed and all of that fun stuff. So the region of normal command just means that as the airspeed decreases, the total drag also decreases to a certain point, okay? And then in the region of reversed command, that is below this point is where the drag begins to increase. And then that means that slower airspeeds require a higher power. So that would be functioning behind the power curve in the phases of flight, such as practicing slow flight at higher altitudes and or being in the traffic pattern while slowing that airplane down. We're going to be working behind that power curve at that point. So we would actually at that point then use pitch to control our airspeed. And our power is going to be whether we stay in the air, higher or lower in the air, our altitude then at that point when we're functioning in reverse command. Okay. Airfoil design, the camber, again, that's that curvature of the surfaces, whether it be upper or lower. We've seen this image before. We're just going back over it again. So the leading edge and the trailing edge, again, the front and the back. So the leading edge is generally rounded. And then the trailing edge is generally narrow and tapered and, pointy, if you really get down to it, look at the picture. So the chord line is just a straight line drawn through that airfoil, connecting the leading and trailing edges. And then the distance of the chord line to the upper and lower surfaces actually denotes the camber then of the wing. And then again, that mean camber line is just equidistant at all points from the upper and lower surfaces through the wing. So it's kind of that average of that curved shape of the wing throughout. So looking at the design characteristics of airfoils, you can see on the right-hand side there are several different types of airfoil ideas and design ideas over there. But what we do know is low pressure rests above the wing, and that's that faster moving air. I'm following Bernoulli's principle, creates a low pressure above the wing. And then a downwash is every action has an equal and opposite reaction as according to Newton's third law. So that high pressure below then, that means the air is deflected now back to Newton's third law, and it pushes up on the wing to create lift, okay? And then the stagnation point, again, is back into Bernoulli's principle, okay? And then we're going to look at the aircraft weight, speed, and purpose to dictate the airfoil design. So again, there's several different airfoils designed on that picture on the right-hand side, and as you progress farther into aviation, you will learn more about the designs and the different wing types. All right, so now the other thing we have to think about too is the differentiation in pressure. So the pressures on top of and below the wings, that's actually going to change with the angle of attack or how we put that wing into the wind. And that's something that as a pilot, we directly control with our yoke or that steering wheel inside the airplane by pushing it forward or pulling it back. Okay. So we are basically, in a nutshell, we're kind of moving the center of pressure on that wing essentially to change how we create or decrease lift. Okay, so the center of pressure, if we pull our yoke backwards, it's going to be a higher angle of attack, which means our center of pressure is going to move farther forward. And if we push the controls forward or the yoke forward, we're actually going to move that center of pressure backwards or aft. And that then in turn does affect that aerodynamic balance and controllability of the aircraft. So if we pull the yoke too far back and the center of pressure comes so far forward that the airflow over the wing is disrupted, we can get into what's called an aerodynamic stall, where the wing no longer has the ability to create lift, okay? So now the plan form is just a fancy way to say the shape of the wing or the outline of the wing if we were to be looking down from above. And this does vary with the desired aerodynamic characteristics or what the plane is going to be designed to do, okay? So the taper then is going to be the ratio of the chord from the root to the tip. So you'll see like a tapered wings or different things over there on that picture, or pointed wings or swept-back wings. That picture on the right there is just the different types of wings, okay? And then the aspect ratio, that's the ratio of wingspan to chord line. So the higher aspect ratio decreases drag and vice versa, and then low aspect ratio for extreme maneuverability and strength, okay? And then again, the swept-back wing is usually swept rearward, but it can be forward, but it just helps with lateral stability in low-speed planes. Okay, so moving on and looking a little bit more about that, then let's talk more about that stability we just mentioned, and let's kind of get into a few more details there. So the inherent quality to correct for disturbances and get that plane back to its original flight path. You know, a lot of these planes just want to fly. So for the most part, if something happens and you let go of the controls, most airplanes we fly in general aviation are going to want to get back to just their normal straight and level flight, okay? We will have to have some inputs at some times to correct them, but for the most part, I mean, they just want to fly, okay? So our static stability then, that's the aircraft's initial tendency when it's disturbed. So if it has a positive static stability, it just returns right back to its original state, okay? If it's a negative static stability, that means it's trending away from that original state. So then we do have to have some input corrections to bring it back. And then neutral. A neutral static stability just means if I pull the yoke back and we start to climb and I let go of all the controls, we're just going to remain right there in that climb where we're at. It's just going to stay put, okay? Now, the dynamic stability would be the response over time when something is disturbed, okay? So again, it's positive, negative, neutral, and it's the same as static stability, but now it's over time. Okay, and you can see the graphics here on the different type of oscillations with how the airplane is working, and it'll show you whether it's positive static or positive dynamic, etc. when you look at those graphics, okay? And again, take a moment to pause the video and study those if you need to or want to. But then again, the stability and controllability obviously significantly affects that controllability and then in turn the maneuverability of any aircraft that you're flying. So continuing on the lines of stability, let's look at the longitudinal stability. And let's talk about the lateral axis, which is the pitch, the elevator controlled pitch, okay? So in a stable aircraft, if the plane is nose to down, the wing and tail moments bring the nose back up and vice versa. And that's dependent largely on three factors. So the location of the wing relative to the center of gravity, the location of the horizontal tail relative to the center of gravity, and then the size of the tail's surfaces. Okay, so continuing on stability, now let's look at the lateral stability. So that's going to be the roll axis or the longitudinal axis. So that's talking about the bank. So looking at the dihedral, that's actually going to be the upward angle of the wings from the root at the fuselage or body of the airplane out to the tip. Okay, so they might angle up a little bit from the body. Okay, and you can see that. It's very easy to see if you look at a Piper on the ground. And if you look at a Cessna on the ground, you can see it a little bit, but not quite as evident as on the low wing, okay? You look at a sweep back wing, and it basically increases the effects of a dihedral. So they're going to have a little bit of dihedral, but they're going to have a lot of sweep back on those wings, okay? And then there's a keel effect. It just means a greater portion of the keel is above and behind the center of gravity. Okay, and then weight distribution. The plane will bank toward the heavier loaded side is kind of how they generally act. The other thing too sometimes is the airplane will be more susceptible to banking to the left for the most part in single prop engine airplanes just because of the left turning tendencies of the propeller. So then the directional stability here about the yaw or the vertical axis, that's that tail rudder that controls that. It's just area of the vertical fin and fuselage aft of the CG, and it acts like a weather vane. The nose wants to point into the wind, so we have that rudder control to help us with that yaw. So then the turning tendencies we talked about, that's that torque effect or that torque reaction. So again, that's that Newton's third law. So the engine parts of the propeller rotate to the right. So then an equal force rotates the whole plane itself to the left. And that's just as that propeller is coming down to the right. It just takes a really big bite out of the air, and it wants to just push that airplane in the opposite direction, as according to Newton's third law. And then also, we do have what's called a corkscrew effect as well, and that means the prop rotation sends that air spiraling aft, and then it ends up striking the left side of the vertical stabilizer, which also helps push the nose of that airplane in the direction to the left. So the P factor is just asymmetric loading. That's the descending prop blade taking a bigger bite of the air that we just talked about as it's descending versus the ascending blade. And then we also have to deal again with that gyroscopic action of precession, because that propeller is spinning on a plane, right? So again, we learned about that gyroscopic precession, and the propeller does the same thing. So it is going to be more prevalent or prominent in a tailwheel aircraft when the tail is raised up for takeoff. And the load factors, go ahead and look at that chart. There are oftentimes at least one or two questions about this when you go through like the written examination for private pilot. So it is good to know and understand how this chart works too. And it just shows you the ratio of the total air load to the gross weight of the plane, and it's measured in G-force. So it kind of tells you where your speeds are in the normal range and how to operate. So any of these charts that you see on here, just make sure you're familiar with them and understand how to read them. If you have any questions, go ahead and send us a message or talk with me in person if I'm also your flight instructor, or talk to your flight instructor if you're just using our ground school and you're flying with someone else, okay? So the very important notes to take away here is it's possible to overload that aircraft's structure, and we don't want to cause damage to that. And you can see the orange areas where we'll have structural damage, and then the red areas, if we get in there, we will actually have a structural failure, which could be catastrophic. So, and then again, also notice that when you increase the load factor, that increases your stall speed. Now that can get kind of confusing, because that doesn't mean it really does get kind of confusing. The easiest way to describe this is if you increase the stall speed, that means the airplane will quit creating lift at a higher airspeed. So that just means it's a little bit more dangerous. Okay, so the load factors on an airplane then, we talked about the structural damage, structural failure. Now let's look at the airplane design. So our normal aircraft are designed to withstand Gs from negative 1.52 to 3.8. Utility category loaded airplanes then can withstand negative 1.76 to 4.4 Gs. And then your acrobatics and aerobatic aircrafts can withstand Gs of negative 3 up to 6 Gs. Okay. And then again, looking at this VG diagram, you're just going to look at the lines of maximum lift capability. We're going to pay attention to that maneuvering speed, the intersection of negative limit load factor and line of maximum negative lift capability, and then our limit speeds. And that again is just to keep everything safe. We've got green is good, yellow, be careful, orange is bad things are about to happen, red is you're dead. Okay, looking at wingtip vortices now and how they work and why they occur. So basically, we said there is like some induced drag, and drag is produced with lift. We can't get around it. If we produce lift, we do produce drag. So they occur whenever an airfoil is producing that lift. Okay, the difference in pressure above and below the wing results in a fast spinning vortice off the wingtip. So, and it's kind of like a mini tornado coming off the wingtip of very disturbed air. Okay. They increase induced drag due to energy spent producing that turbulence. Okay, so the greater the angle of attack, the stronger the vortices, and they are the strongest when your plane is heavy, clean, which means we're not using our flaps, and slow. Okay, heavy, clean, and slow creates the largest amount of wingtip vortices, and they can be very, very dangerous to small aircraft if they're coming up a bigger aircraft. So the vortex then, they will sink at several hundred feet per minute. And at the ground, they tend to move with the wind. So in a crosswind, it'll actually decrease the movement of the upwind vortex. It decreases the movement of the upwind vortex, and then it'll increase movement of the downwind vortex. Okay. And if you have a tailwind, it can actually move the vortices into your touchdown zone. Okay. So you can see, it says in this picture, we can see visible vortices in the water. So you can see them kind of pushing the water, their crosswind from the right, blowing the vortices to the left. So that's what that picture is. That disturbed water there off the end of that right runway, 28 right, that is a good depiction of what they would look like if we could see the wind, okay? So avoidance, pretty easy, actually. You just take off prior to an aircraft's rotation point, and then you climb above their flight path. Now, if you're in a small airplane, it might be hard to outclimb a jet. So then let's just wait, anywhere from 4 to 6 minutes before you take off. That's the easiest way, okay? But again, then you take off after, and if it's a landing jet, then you take off after their touchdown point, because once they're on the ground, they're no longer creating lift. So you taxi past that, take off, roll past that, and then take off after their touchdown point, okay? If you're en route, avoid flying through another aircraft's flight path within 1,000 feet. Okay. And again, land prior to a departing aircraft's takeoff point. So land before their takeoff point was. So note that. And then stay above a preceding aircraft's path and land beyond their touchdown point. All right. So now we have some additional info for the principles of flight that we'll just quick go through. We're about 75% of the way through this lesson. So this one's been a little bit quicker than our last one. And then you'll be done with the first portion of the ground school for private pilot. So nice work there. So on the overview, we're going to look at the forces of flight and how they affect the airplane during different phases of flight. Why? Well, it's how a pilot performs in flight depends on the ability to plan and coordinate the use of power and flight controls to change the forces of lift, thrust, weight, and drag. The pilot must always control a balance between these four forces, and the better the understanding of the forces, the greater that pilot is going to be in the cockpit as a pilot for both safety and having fun flying, okay? So we'll talk about ground effect, climbs, descents, turns, and then stalls, okay? So ground effect reduces induced drag. It's the vertical component of the airflow around the wing is restricted by the ground. So that's basically when we're within a wingspan of the ground is what we call ground effect. And then our vortices will hit the ground and they don't have anywhere to go. So we get a lot more lift, and it seems and feels like the aircraft responds a little bit better to us, okay? So on takeoff, capable of lifting off at lower than normal speed. And then on landing, it seems to float when we get in ground effect. So those are all things that we need to know and anticipate, and we can use them to our advantage as well. All right, so climb entry now. In a steady climb, lift is the same as it is in level flight at the same airspeed. Raising the airplane's nose to increase that angle of attack, that's going to momentarily increase the lift. Once the climb's established, an angle attack and lift will return to level flight values. So level flight, normal lift, climb entry, increased lift, climb entry, steady, normal lift, okay? Climb airspeed. Now, with no change in power, airspeed is going to decrease in a climb. When we're inclined upward, a component of weight acts rearward and has the same effect as drag. So additional power is then going to be necessary to maintain our airspeed. Conversely, lowering the nose momentarily reduces angle of lift. Lift is momentarily less than the weight, changing the flight path. Once stabilized in the descent, the angle of attack and lift return to level flight values. And with no change in power, airspeed is going to increase in a descent, and a component of that weight acts forward and has the same effect as thrust. So power must be reduced to maintain. All right, so the lift and angle of attack in turns. So lift is divided into a horizontal and vertical component. So the vertical component acts vertically, and that's opposite weight, And then the horizontal is actually what's making the plane turn. So that's the centripetal force. So in a turn, the angle of attack's vertical lift is reduced while weight remains the same. And the angle of attack has to be increased so the vertical component of lift equals weight. Increased angle of attack also increases drag because, again, we're creating a little bit more lift, so we're increasing drag. So we have to have some power added back in to maintain our speed. So looking at the graphics below, you can see the horizontal and vertical components while turning with and without back pressure. It's showing you to the left there, but the same applies to right-hand turns as well. All right, so turns and turn radius, rate and radius of turns. The rate of turn varies with the horizontal component of lift, or the bank. And then the turn radius, that actually varies with airspeed and bank angle. Okay, so again, there's those graphics down there, and it's going to tell us what it looks like, whether we're coordinated, slipping, or skidding in a turn. Okay, and we always want to stay coordinated if we can, unless we purposely enter a forward slip, which is a maneuver you will learn as we progress through your training. So first, the coordinated turns, just the horizontal component of lift. That is the centrifugal force, not centripetal, but centrifugal. Now, a slipping turn, the rate of turn is too slow for the bank angle, so that horizontal component of lift is greater than the centrifugal force. Okay, and a skidding turn is the opposite. The rate of turn is too great for the bank angle again, but centrifugal force is greater than the horizontal component of lift. So if you've ever been to watch dirt track racing, when they whip the back end around the corners, that's a skid turn. Think of the same thing in an airplane. And a slipping turn would be the tail's not going around, you're dragging it around with you. So now let's talk about the basics of stalls, and we're just about done with this portion, I promise, but let's talk about the basics of stalls. So again, we keep talking about this angle of attack and stalls. Well, a stall in an airplane is not the engine quitting. We're referring to an aerodynamic stall, which means the wing is no longer creating lift. Okay, so this is a direct cause of all stalls is due to an excessive angle of attack. Okay. Now, a stall can happen at any airspeed and at any attitude, so that you have to remember from the start. The stall speed is going to vary based on several different factors of the aircraft, weight, different things like that. But the angle of attack for a stall is always the same, and it's generally somewhere between that 16 to 20 degree of pitch neighborhood, okay? But again, that stall speed can vary whether or not you have picked up ice or you have things loaded differently inside the cabin area. I mean, so that the stall speed can vary, and it will. But the stall angle of attack is always the same. And like I said, again, it's going to be somewhere between that 16 and 20 degree mark. So in the phases of flight, again, a stall can occur in any phase of flight, at any airspeed, at any attitude. So let's talk about low speed for a minute. As the airspeed decreases, the angle of attack must be increased to maintain that altitude. But we also know that if we get between 16 and 20 degrees of pitch or angle of attack, we know that we could cause that stall. So we have to be mindful at low speeds that now we are working with behind the power curve at a super low speed. So as that angle of attack increases, we need to increase our power to make sure that we have enough speed to keep lift created under the wings so the wing doesn't stall. Now, when we're at high speeds, high speed dive, if we're in a high speed dive and do a sudden increase in back pressure, we can actually forcibly cause those wings to lose their lift as well and stall out on us there. And then when you're turning, stall speeds are actually going to be higher, which means you'll stall at a higher speed. So you're going faster than you normally would in a straight and level stall. So when you're turning, these stall speeds are higher in a level turn than a straight and level flight, and the wing has to produce additional lift to counter the load imposed, or that increased load factor from that turn. Okay, that's the end of this chapter, which marks the end of the first section, which is lesson number 1 for the Private Pilot Ground School. Again, if you have any questions, feel free to message through the website. And if I am your in-person CFI as well, you can ask me the next time we get together. And if you have your own flight instructor, or you're just doing the ground school with us and you go to school somewhere else for your flight lessons, do ask them as well. We all teach a little bit differently. So the way I understand something might not be the way you understand it. But if you don't ask a question, we can't find a way to get that through to you to understand it. So we're all about teaching, learning, educating each other, and staying safe. So appreciate you riding with us on this flight. And until next time, stay safe.